Just to comment that we had a little change in the schedule, so the talks of the afternoon, they will all shift a little bit earlier. So if you're talking today, just check the updated timetable is in the web page. So it's the same talks, but a little bit earlier, okay? So let us start with Alejandro Ayala. She'll have some magnetic fields in the afternoon.
Thank you, Anna. And I also want to deeply thank you and thank Giorgio and the organization of this conference. It's a very nice setting, and I've always been received here as at home. So I'm spending a sabbatical year, and on top of meeting friends and a nice working atmosphere, it's fantastic science. So thank you very much. The subject of the talk has to do with the search that most of you working in this field are conducting to find some probes that finally capture definitely the presence of magnetic fields in heavy ion reactions. Now, these are difficult probes because, as you know, the heavy ion collision is an untamed beast, and it produces many signals, and there is a lot of them which get entangled. And so finding a probe which carries out the information from the reaction zone is challenging, and what we want to do is to put some words on that direction. And what we were discussing or have been discussing lately is how we can look at the emission of dileptons, particularly dimuons, from Z decays that come from early in the collision in the presence of a magnetic field. This is work done in collaboration with Anna and Javier Rendon, a postdoc in my group that is also here in the conference. And you can find, if interested, details in this preprint. So this is just a slide of introduction. We know that heavy ion collisions are an excellent tool for exploring the properties of other matter subject to extreme conditions. And these extreme conditions include not only high temperature or density, but also the possible presence of electromagnetic fields. But I think that in all fairness, in spite of the many efforts aimed at identifying clear probes directly linked to the presence of these fields, up to now, the clearest signal comes from the detection of the linear bright-Wheeler process in ultra-peripheral collisions. So these are not central collisions or semi-central, these are ultra-peripheral. So this is depicted in this cartoon taken from this reference. So one nucleus moves in one direction, the other one in the other direction. The impact parameter is larger than twice the radius of a nucleus. And so because these are intense fields and they are perpendicular to each other, the electric field is perpendicular to the magnetic field, then the photons are linearly polarized, and then if you detect them, you can associate these photons produced by these fields from this process. So, of course, there are other attempts to try to pin down what are other signatures of the presence of these magnetic fields. And here I just took a couple of examples. There are many, but from this reference some time ago, there was the calculation of the synchrotron radiation in the QGP. And well, the author argues that the total spectrum computed from this process cannot be accounted for, but nevertheless it gives a good contribution to it. Also, you can, this is also a nice calculation, that in a magnetized quark-gluon plasma, a magnetic field enhances the dilepton rate and the ellipticity at small values of the invariant mass. So this is just the dilepton rate. I mean, if this is the invariant mass of the dilepton pair produced by quark-antiquark annihilation, through a photon, then if you observe this, then you may get some indication that this was produced by the presence of these magnetic fields. Just to give another example, of course, colleagues have looked at the Z zeros and charm in the QGP, and these are, of course, good penetrating probes because they are produced early in the reaction, but they looked at them on the QGP side. So the dileptons that originate from the decays of the Z0 produce a splitting of V1, and so these are theoretical calculations in the charm or in the Z, and so this could be another option to detect these fields, but I stress that this is computed in the QGP. Later, and more recently, some other calculations have looked at the possible changes of the spectral density of the Z as you vary some parameters of the calculation. For instance, the time at which the emission of these dileptons happens, and for very large values of the magnetic field, and this is aimed to compare to lead-lead collisions at some impact parameter at 5.02 TeVs in the LHC. So this could be also another possibility. But let me then come to my point. If we want a chance to detect this, the influence of the magnetic fields on probes, we want that these probes are penetrating to begin with, and second, that they are produced at the very early stages of the reaction. Because you see, this is taken from an old paper, but nevertheless it illustrates what I want to say. The field, as you know, decreases very rapidly with the time after the collision. So by the time you have quark-gluon plasma, which is sort of nearby 1 Fermi after the initial time, then the field intensity has gone down by almost 3 orders of magnitude. So it is complicated that on top of that, if the probe has to go through the mess that happens during the collision, then that the probes can be carrying out the information in an unambiguous way. And I also want to stress that we want something which is easily linked to the presence of the magnetic fields at the early stages of the collision. So, in fact, we've been looking at those possibilities also with electromagnetic probes. What we looked not long ago, and as a matter of fact, Santiago Bernal will later on during this meeting will speak about that during the flash talks. We looked at the production of photons from gluon fusion in a magnetic field. So this process is not allowed in vacuum, but it is allowed in the presence of a magnetic field. That is because if you sum up these two contributions, Furry's theorem doesn't apply anymore. And so these will give you a different from zero contribution in the presence of a magnetic field. And then you can try to sort out what is the what happens. And what happens, of course, is that V2 is different from zero. It's positive, and it is strong as, for instance, depending on the parameters of the model. It is as strong, for instance, as V2 of the pions. So this is a good feature. And if you look at the process at the very beginning of the collision, where there are lots of gluons, more than quarks, then this should be a dominant contribution. And also the field is as intense as it gets, because it is at the very early stages. But still, this is not easy, and so the idea is to have a better battery. That would help. Okay, this is the time. Yes, please. No, the microphone is not the problem. The problem is this. No. Okay. Questions? Excellent, thank you. It is. All right, so with this introduction, what I want to stress is that if we look at pre-equilibrium, the magnetic field must be at its highest strength, and since hard probes are also produced at the very early stages of the collision, if we look at the electromagnetic probes produced by these hard probes, like the Z0, then these dileptons can potentially carry out the information of the strength of the magnetic field at that time. So for that, then the idea is to look at that process. So let me put the calculation into perspective. I will give you some details, not very many, but in any case, since there will be a discussion session later, we can discuss details. So imagine that you have nucleus-nucleus collision, then you have a quark and an anti-quark in this nuclei that collide at some space-time point x, and they produce a Z0, then which later decays into a pair of muon-antimuons at a certain other point y, space-time point y. And so what we want to look at is the current correlator describing the production of Z0 from this process. And then the point is that if we want the probability, then what we need to do is to square this amplitude. So to square the amplitude, then what you need, this will give you the number of dimuons per unit volume and time. And the calculation can be simplified because if you square, then you can factorize this process into a hadron tensor, which is this one in the hadron side and a lepton tensor in this side. And so I will just walk you through the calculation of both parts. So the hadron side is can be expressed in terms of the polarization tensor for the Z0. And what we will do is to work in the lowest Landau level approximation. Now, why do we want to do this? It may be possible that there are contributions from other Landau levels. This is certainly true. And in fact, the calculation for the photon decaying into the muon-antimuon pairs carried out by Igor shows that the contributions from other Landau levels may be important. Now, in this case, what we want to do is to have a feeling of whether or not this kind of calculation at least makes sense to find a smoking gun to see if we can later on refine the calculation and see whether the influence of other Landau levels or some other assumptions that need to be relaxed will provide a better description on top of what we possibly find. So for that matter, we will work in the lowest Landau approximation. And that means that the physics is going to be one-dimensional. There is a dimensional reduction, as we all know. So everything is going to be described in terms of the parallel components of the forward vector of the Z0. So these are the 0th and 3rd component of the momentum of the Z0. So what is the process? The process is two quarks come, annihilate. There is a magnetic field going in this direction, so the quarks move around, they annihilate, but because they are constrained, tightly bound in this magnetic field, they go like this. They produce a Z. The Z moves in a certain direction, which is parallel to the magnetic field, and then the two muons come out, one this way and one the other way. I'll show you. So this is what I want to compute, and you carry through. And because of this assumption, the calculation is transparent. If you don't make these simplifying assumptions, then sometimes you can get lost, as probably many of you know. So the summary of the result is that the polarization tensor can be expressed in terms of two polarization tensors. This is one of them. It is called the parallel polarization tensor, but it is really transverse to Q parallel mu. So if you dot Q mu with this tensor, then you get 0. Whereas the other one is longitudinal to Q, at least to the third component. It has a projection in the third direction. So this is longitudinal, and this is perpendicular to Q. And the usual definitions of G parallel and Q parallel and Q perp are these here. Here. Okay. So the calculation, the rate, requires the imaginary part of this tensor. And the imaginary part is given by this expression. What I want you to notice from here is that, of course, there is the usual threshold signaled by this theta function, but moreover, that there is one of these factors that dominates the process, because Ca squared, this is the axial coupling of the quarks to the Z boson, is much larger by an order of magnitude than Cv squared. So in that sense, this is already signaling that one is going to dominate over the other. And let me go back and show that, as I mentioned, Cv will come with this structure, the PL. And so that means that the polarization parallel to the direction of motion of the Z is going to dominate over the transverse to that direction. That is important. Yeah. Mrs. Chairwoman, can I have 5 more minutes because of this? Please. I can take questions if you want. So far, so good.
It works? Yeah.
Okay, I'll proceed.
Make it work again.
I'll proceed. It was because Giorgio moved. People upstairs were scared when he was running up. Okay, so you also need the real part. Now, as it is working, but please do, yes. So the real part is also important because, as I'll show you, if you imagine, thank you, if you imagine that the Z spectral density is that of a resonance, then the mass of the Z will be influenced by the real part of the polarization functions. So this is the expression for it, and as I told you originally, if you're looking for analytical guidance, there is nothing nicer than something which is analytical in this sense. So again, the real part of the parallel part here comes out to be, again, well, it has both components, but the longitudinal part has is the dominant one, and it's the proportional to Ca squared. Okay. Now, to sum up, the hadron part is given by this relativistic Bright-Bickner expression, and I emphasize that this is the relativistic one. Now, you can also make an approximation which is non-relativistic, but for these purposes, I think that the best way to think of the spectral density for the Z is in terms of the relativistic expression. Now, the magnetic field comes in here in the imaginary part of these polarization functions. For the width, the imaginary part is what matters. For the mass, it's the real part. Now, let me go back slightly to show that there is a strong suppression factor in front. This strong suppression factor is the ratio of the quark mass squared to, if you're looking at the process at the Z peak, this will be the invariant mass of the Z. So this is way too small. And if that is the case, then there is very little chance that the real part will do anything to the mass, neither the imaginary part to the width. And therefore, any signature of this process in this approximation has to be looked for not in the modification of the mass and width of the Z, but instead we need to look at some properties of the spectral function of the dileptons. So let's go to that part. That requires to look at the lepton tensor. And for that, what we recall is that these leptons are moving in a magnetic field. And if they are moving in a magnetic field, then they are not plane waves. They need to be described by these Ritus functions. So we work in the lowest Landau approximation, for which these functions are just Gaussians that tell you that the probability that the leptons are found near a field line is the largest. So they are circling around the Landau level. Oop, I'm gonna have 5 more minutes, is that all right? Sorry. Okay, so you can work in any gauge. This calculation is gauge invariant. We decided to work in gauge, Landau gauge 2. Yeah. Here. Yes, thank you. All right. So let me just sum up what is the result for the lepton side, and this is an expression which is actually very familiar to everybody, except that again there is dominance from the axial coupling of the Z to the dimuons, and that because there is a gamma 5 involved in the calculation, changes this sign, and this is important. Also, because momentum is conserved only in the third direction and energy is conserved, but not in the transverse directions. There is no delta functions in the transverse directions. So the result for the rate as a function of the invariant mass is this nice expression right here. And again, this comes from the lowest Landau level approximation in the lepton sector, and the probability is proportional to EV squared from the quark from the muon side, and there is another extra factor of EB here from the imaginary part of the hadron side. Okay, so since the dimuon and the quark charges are involved, this factor A here is this combination. Okay. Okay. So first thing, because of that dependence, we can compute the V2. And the V2 is computed from the azimuthal angular distribution, and it's given by this expression. And if you compute it, then you get also a nice analytical expression, which is negative. So V2 is negative, and I'm here contrasting with the recent measurements from Atlas that shows that V2 is compatible with 0, but if you are well-intentioned, then you can see that as the centrality increases, this trend actually shifts towards, or at least the central value shifts towards negative values. Again, these measurements include both photons and Z's, and we were told by our CMS colleagues that this is just because the statistics is low, but they can disentangle Z's from gammas. Okay, so this is the first result. The second result is the, oops. Sometimes it works if you do this. Can they change it manually? There. So what is the process? What is the process? Quickly. So there is, the first thing to remember is that the polarization of the Z, which is depicted by the direction of the spin with respect to the direction of motion of Z, is mainly along the direction of motion. So the upper row here is the case in which the Z moves in the positive direction, in the direction of a magnetic field, and here it moves opposite. So let me just concentrate on this because it's just a mirror reflection. So if I do that, then the next panel shows the spins of the muons that come out from the Z0. So both have to be pointing up because, well, that was what this spin was doing. But see, the muons are almost massless. So they are almost in a chirality state. And so because of that, the anti-muons should be right-handed and the muons should be left-handed. So because of that, then, and because here, if there is a small momentum in the third direction here, then what happens is that the momentum of the muons is going to be larger than the momentum of the anti-muons is going to be larger than the momentum of the of the muons, and this should reflect in the dilepton spectrum. So, of course, we need to reconcile this picture with the occupation of charged particles with spin in the lowest Landau level, but the important thing to remember here, and we can discuss that later if you want, probably I won't have time right now, but later in the discussion session, there is a relaxation time for that to happen. So instantaneously, thank you, instantaneously, the weak decay makes these muons and anti-muons come up in this chirality basis, but after relaxation time, of course, these spins will point out in the direction they should in the presence of a strong magnetic field. All right, so let's put some numbers to see how this works out. I want to look at the dimuon invariant mass distribution. So I need to know how many Z's are produced, and this is just a parametrization that you can find in this paper with these parameters right here. So let me show you the picture, and I'll come back to these numbers. Come on. Aha, here. Anna starts walking and everything works. All right, so this is what I was telling you. On average, the anti-muons come out with a harder spectrum than the muons. So the peaks are separated. So the mu plus peak is displaced over larger values of PT compared to the mu minus peak. And the separation, in fact, is proportional to the inverse of the parameter C that controls the way the Z's fall down, their distribution falls down as a function of PT. And it turns out to be of the order of 2 GeVs. So 2 GeVs for the capacity of these detectors is something which I believe it is feasible. And also the ratio of the mu plus to the mu minus distribution is greater than 1 for PT larger than the position of the peaks. So that is also something to look for experimentally. So let me just come up to the conclusions here. First, the summary. The search for signatures of the presence of magnetic fields in heavy ion collisions is a challenge because there are many sources of background, particularly if looked for with probes with imprints in the QGP. So more promising probes are those produced during the early stages of a collision, which is called pre-equilibrium, where the field is also at its highest intensity, and electromagnetic probes being penetrating are more likely to carry the imprints of the putative magnetic field. And there is only 2 slides, so please, come on. I know. Come on. Here, no. Here, all right. So what we did was to study this process, the decay of Z zeros on the muon pairs, and we looked at the properties of the individual muon distributions near their peaks. And of course, as I mentioned before, more refined studies are needed to include the relaxation of the strong field limit, and we are currently exploring such venue. And with this, I thank you, and if the projection allows me, I will also thank the sponsors. Thank you very much.
Questions? Ooh.